Welcome to the Phenomenological Alliance channel. In this video, we will explore the challenges of expressing concepts of physics through mathematical formulations.
Sir Isaac Newton is widely regarded as the spiritual father of modern mechanics, and his laws became the cornerstone for all mechanical principles in the following centuries. Newton's laws of motion describe the relationship between the motion of an object and the forces acting on it. These laws can be expressed as follows.
A body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by a force. The net force on a body is equal to the body's acceleration multiplied by its mass. If two bodies exert forces on each other, these forces have the same magnitude but opposite directions.
The phenomenological methodology always proceeds from first-person experiences. Accordingly, let's keep in mind that the fundamental concepts in mechanics, force, speed, and acceleration, are basically perceived through senses of touch, sight, and balance. Statics, kinematics, and dynamics, as the main branches of mechanics, have evolved from the perception of mechanical phenomena through these senses. With such an insight, let us examine Newton's three laws of motion. In mainstream physics, force is often defined as an interaction that changes the motion of an object. According to Newton's third law, forces always appear in pairs. For every action, there is an equal and opposite reaction. When we push on a wall, our finger exerts a force on the wall, and the wall exerts an equal and opposite force on our finger. First and foremost, a phenomenological approach emphasizes the differences in the physicality of various mechanical forces. Static pressure forces, perceived by the sense of touch, are contact forces that generate reactions such as a static stress. Dynamic forces of imbalance, perceived by the sense of balance, have a different underlying physicality, as they are fundamentally connected to states of imbalance. The description of static pressure forces that occur in pairs should emphasize that the fundamental characteristic of statics is the equilibrium of forces in a state of rest. Pushing a static wall creates material tension, while pushing a movable object leads to an imbalance, manifesting as acceleration. A literal application of Newton's postulate to all mechanical problems obscures the fundamental difference between the nature of static and dynamic reactions. This matter may seem like a witty quip, but it becomes serious when the same conclusion is applied to circular motion, where centrifugal force is declared an illusion. In a uniform circular motion, there is a constant imbalance, not an equalization of forces. It is not about state of rest, but about the state of imbalanced motion. The phenomenon of imbalance is inherently linked to the appearance of force pairs with differing intensities. When considering the relationship between force and acceleration, in Newton's axiom, mass serves as a link between them. But for real bodies and terrestrial problems, this is valid only when the body is in a state of weight. When the body is buoyant, this constant changes. The constant in Newton's second law, postulated as mass, in real-life situations becomes a variable quantity. Newton's second law postulates that force and acceleration must have the same direction, overlooking the fact that acceleration represents a state of imbalance. Newton's approach attempts to solve the problem of dynamics, specifically the appearance of forces in a state of imbalance, by relying only on the perception through the sense of sight. But perception through the sense of sight cannot reliably inform us about forces as forces cannot be perceived by sight. When modeling mechanical problems mathematically, it's crucial to know whether the principles of kinematics or dynamics are applied. It's necessary to be aware of whether the model is based on perception through the sense of sight or the sense of balance. For instance, in ancient mechanics, the lever problem was solved using the principles of kinematics without considering force and mass.
Why, when the yard arm is higher, does the boat sail faster with the same sail and the same wind?
A lever must have the same speed on both arms. A large motion on the long pole causes a small motion on the short pole.
The problem of inertia contains two questions: perpetual motion without driving force, and the stability of uniform rectilinear motion. Basically, perpetual motion is a cosmological question of whether there is a driving force on the planet. In the vortex theory, the vortex of cosmic ether was believed to drive the planets. In Newton's gravitational model, there is no driving force. The planets move by inertia. In Aristotelian physics, motion is always contextualized within a medium rather than empty space. The problem of inertia is intertwined with the philosophical debate concerning the existence of vacuum, namely, whether space is truly empty or always filled with something, either matter or a field of forces that drive planets. The question boils down to whether a body can sustain rectilinear motion in vacuum, or if its trajectory will eventually curve. On the other hand, terrestrial inertia is a concept grounded in a thought experiment, as no terrestrial body can sustain perpetual motion. If we summarize the phenomenological analysis of Newton's laws of motion in real-life situations, we can conclude: the emergence of force pairs is a fundamental problem of stability. In real-life situations, dynamic force pairs are of equal magnitude only if the system is stable. The relationship between force and acceleration in real-life situations is governed by a constant, which represents the mass of the body only under conditions of a rare medium. In real-life situations, inertia indicates that bodies in curvilinear motion always tend towards equilibrium, which is achieved in uniform rectilinear motion.
Phenomenology is defined as the science of conscious experience. When applied to consideration of mathematical formulations, the phenomenological approach emphasizes the significant difference between numerical formulations in mathematics and those in physics. In mathematics, numerical formulations refer to the laws of numeric entities. For example, the relationship between mass, acceleration, and force can be expressed by the formula F is m multiplied by a, or a is F divided by m. No formulation violates the numerical laws. In contrast, physics is not a logical discipline, but a natural science. The formulation F is m multiplied by a expresses that a body with mass m and acceleration a produces an impact force F. The formulation A is F divided by m states that a body with mass m, when acted upon by force F, will have an acceleration a. In physics, numerical formulations reflect underlying convictions and philosophical concepts, frequently demonstrated through thought experiments. However, expressing these ideas mathematically can obscure their true essence. Instead, mathematically formulated thought experiments often give the impression that these formulations represent the objective description of reality.
After briefly describing the difference between mathematical modeling and physical principles, The next video will explore how understanding these physical principles can be applied to the problem of gravity.